we're going to continue to look at solutions to differential equations or systems of DEs. And there's going to be more examples and kind of codifying some of the things we discussed and seeing what it implies in terms of finding our solutions. To recap, what's important is if we have a system of equations, and we're assuming that we're working with a square matrix for matrix A, then this is a big if we can find n independent eigenvectors, then our solution looks like a constant times e to the lambda 1 t v1 plus a constant times e to the lambda 2 t v2 all the way out to the last one. And we found that if we form a matrix V, where the first entry is the first eigenvector, second entry is the second eigenvector, down to the end, then if we're given an initial condition, that's equal to V times a vector made up of our unknown coefficients. And we can solve this as a linear system using the reduced row echelon form of our matrix. Also, if we form another matrix that's diagonal, so it has all zeros except on the diagonal entries, look like e to the lambda 1t, e to the lambda 2t, all the way down to the last one, then our x of t is going to be, what did we say? I always get these two mixed up. So it's going to be down, so it's going to be what? VL times C. Okay. Is that correct? So I'm going to go down, get to 1, then to 2. I think that's correct. Okay. Double check that. I may have misremembered that. Okay. Now, let's just do some examples. But for now, keep in mind if the real part of any of these eigenvalues is greater than 0, our system is going to be unstable. If all of them have a real part that's negative, it's going to be stable. And if we have an imaginary part that's not 0, we're going to get oscillations. And all this is exactly the same thing that we saw before. The only thing that's different is that all of them have to be negative for the real part. And if any one is positive, it's unstable. The only difference is we're dealing with more of these numbers. So let's look at an example. Suppose the derivative of x is equal to 5, 24, minus 2, minus 9, x. And the initial condition is 4, 2. All right, I'm not going to go through and do all the computations on this, and you should be able to do this on your own. The first eigenvalue is going to be minus 1, and I found an eigenvector of 4 minus 1. Notice this is not the only way to write this. If I'd written 1 and minus 1/4, it's perfectly valid. The other one is lambda 2 is minus 3, and V2 is minus 3, 1. So notice both of these are real and negative, so it's stable, and this is the largest. So the dominant term is going to be the direction V1, and it's going to decay like e to the minus t. It's really important to be able to identify that. Okay, so our solution then is going to be C1 e to the minus t times 4 minus 1 plus C2 e to the minus 3t, which is coming from there, times minus 3, 1. And now to find the values of C1 and C2, so if I plug in t equals 0, I should get 4, 2. So that's going to be C1 times 4 minus 1 plus C2 times minus 3, 1, because e to the 0 is 1, e to the 0 is 1. I can write this now. The first column is going to be 4 minus 1. The second column is going to be minus 3, 1. Is that right? So my first entry is 4C1 minus 3C2. So 4C1 minus 3C2, so that checks. Second entry is going to be minus C1 plus C2. So I'll get minus C1 plus C2. So that checks. And now to solve this, I can put this into an augmented matrix and put it into reduced row echelon form. All right. We've done this many times, and it's really boring to sit here and listen to me do this. But if you go through and do all of the operations, and those operations are in the class notes on ELC, you should get 1001, 10, 12. And this means that C1 is 10 and C2 is 12. So x of t is going to be 10 e to the minus t 4 minus 1 plus 12 e to the minus 3t times minus 3, 1. Another example. Again, I'm going to go through this quickly like before just to lay out everything that you need to do. Suppose you have the derivative of x is minus 1750 minus 20, 18, and the initial condition is minus 2, 3. In terms of the eigenvectors and eigenvalues, again, you should be able to do this. You don't need to watch me go through and do all that by hand. But you will be expected to show that your first one is going to be minus 2 with an associated eigenvector of 1, 1. And the second one is going to be 3, and that eigenvector is going to be 3, 4. So you should recognize that this one's going to decay. It's going to go to 0 like e to the minus 2t. This one's going to grow like e to the 3t. So this is the dominant term, and this is unstable. Okay? So my solution then looks like C1 e to the minus 2t times 1, 1 plus C2 e to the 3t 3, 4. And now to solve this, for C1 and C2, I plug in t equals 0. X of 0 should be minus 2, 3. And then e to the 0 will be 1. So I'll get C1 times the first eigenvector plus C2 times the second eigenvector. And I can write this. The first column is 1, 1. Second column is 3, 4. My unknowns are C1, C2. So I put this in an augmented matrix. So 1, 3, 1, 4 is equal to minus 2, 3. Okay, you should be able to go through and do this, put this in an augmented, or put it in reduced row echelon form. Again, I'm not going to do this. If you do that, you should end up with minus 17, 5. So this says that C1 is minus 17, C2 is 5. So my x of t is going to be minus 17 e to the minus 2t, 1, 1, plus 5 e to the 3t times 3, 4.